So enthalpy is it's another. So think of it as internal energy. It's sort of like internal energy. It has the same units as internal energy, except that enthalpy is an additional part of internal energy. So, for example, you can just see it right here: is that enthalpy is equal to H or U plus PV, and H is enthalpy. So it's internal energy plus pressure times volume. Okay, so essentially how that works is that enthalpy is equal to the internal energy of the fluid plus the work of the fluid. Because remember, PV is usually work, right? You could say. So enthalpy are those two things added together, and there's a reason why these enthalpy is listed, and it's used all the time. And what it is used in open systems. So really quickly, I'm going to draw you two examples. So right here, this right here, so everyone should pay attention. These two examples are generally where you use enthalpy and where you don't. So let's say we have some water in here, and you're heating it up, right, with some Q. Put some heat in, right? But nothing leaves this boundary. This is a closed system, correct? Nothing is leaving the boundary. This is where you'll use internal energy. Right here. This is an internal energy question. When it's a closed system, you use internal energy as your properties, right? All right. Now, let's say we have the following. So what I have drawn here is the thermodynamic symbol for a turbine. Okay? So this is generally what a turbine looks like. Go back up. So what that means is that for an open system where mass is able to flow outside of the boundary, like for example, the boundary is this turbine, right? Mass is flowing into it and then leaving it, correct? This is where you use enthalpy. I hope that is somewhat clear. So, for example, if I give you a question that is a clear closed system, like it says a closed rigid tank is this, you will use internal energy to find like heat transfer and find all those other things. If it is a system like this, an open system, like a turbine, a compressor, a valve, what's another one? A nozzle and a diffuser. You will use this. You'll use enthalpy for a system like that. Okay? So I'm going to do a little bit of reading here as we make note of that. Okay? So it says, in many thermodynamic analysis, the sum of internal energy and the product of pressure times volume appears. Because the sum of U plus PV occurs so frequently, in subsequent discussions, it is convenient to give the combination a name, enthalpy, and a distinct symbol H. By definition, H is equal to U plus PV. So what happened was essentially is that in thermodynamic studies, like while they were trying to come up with like tables and while they were coming up with like properties and things like that, they found that internal energy was added to pressure times volume a lot. Like it kept showing up in the study. And so because it came up so much, they substituted it. Essentially, they like made a substitution and said, okay, well, we're not going to keep writing it as U plus PV because it gets, tiresome after a while. And so they substituted for a shorter thing, which is H. So they called it a whole new property, which is H. H is equal to U plus PV. And H is enthalpy. All right. All right. And then here, this right here is the same thing we have been going over, so I'm not really going to rehash this. If you guys remember that the X equation, so the quality equation, is equal to, we'll just do U minus UF over UG minus UF. I hope this is ringing some bells. Can I get a yes if that is ringing bells? Hopefully that is something that we remember. So this right here, this equation, this whole this part right here is basically saying that you can use this equation for H as well. So you can remember when I told you that this equation right here, this like all of this can be used for the exact same thing. So you can use H in there. So you can do H1 plus HF times X times HFG, right? And now you guys are probably wondering what HFG is. HFG is the subtraction of HG minus HF. And this is a really fun case, is that if you go to your tables, HFG is usually given to you. It is not given as internal energy, but it is given to you here. So that's pretty neat, is that so when you do the quality equation and you need the subtraction of this term and this term, you can just plug this in there because it is the middle of it. But it does not exist for internal energy at all. It is for enthalpy. It is there for enthalpy, not there for internal energy. So HF is still your saturated liquid value. Hg is still your saturated vapor value for enthalpy, just like it was for internal energy. But they've added a new column for HFG, which is these two subtracted. And you can verify this, right? You could do 0.01 minus this, and you will end up with the one in the middle. So they just added a column for your convenience to help you do that calculation quicker. But essentially, all equations that have applied so far to finding like internal energy and specific volume using quality, they all apply here. Okay, they all apply here. And so right here, they go through a quick example. So you can see they have told you that to illustrate this, you go to refrigerant 22, 12 degrees Celsius, and they gave you its specific internal energy. All right? And so because they gave you the specific internal energy, they want you to find a quality. The quality ends up being 0.5. And then you can go back to your equation for enthalpy and do the a calculation for that, and you end up with 156. So at low temperatures, they will be very close together. Like they should be very close together. As you can see, 144.58 and 156.67, or not low temperatures and pressures. How about that? They should be fairly close. Internal energy and enthalpy should be very close. But as you get higher up, they start to become a bit different. So like as you guys can see here, 50, 41, it's the same for at this temperature, right? They have the exact same. And this right here is the temperature table. So temperature tables, they're all fairly similar. Actually, they are basically the same. Now, if you go to, I think, the pressure table, they start to get a little bit different at some point. Let me see. Yeah. So they do start to get a tad different, but not a whole lot. But it's still important that you use the right value, okay? Yeah, I mean, it's not a whole big a difference. But because think about it, is that the internal energy should be the same thing as this value, except plus that PV term. And generally speaking, that PV term is very small. So U is enthalpy when added, when you subtract, essentially PV is added on to enthalpy. So they should be very similar. Okay? Does anyone need to go over this really fast since it has been a minute? Or are you guys good with the tables to some extent? Kinda good? Like kinda go over it or kinda good? Okay. Okay. Making sure. Because from like here on out, tables are going to kind of be assumed, right? I'm going to have to assume that you guys know basically what you're doing in the tables because we can't spend, 3 more class periods going over tables. We have to kind of assume that you know what you're doing now. All right. So, let me go ahead and move on because that stuff is not really that important. Yes, you will have so what you will have on exam is you will have the full use of the tables, and you will have the equation sheet. The equation sheet will have basically all of these things in it. So like the quality equation will be in it. The work is equal to PdV equation. Everything you could ever possibly need will be on there. So you'll have that. All right. Let me see if this is important. Not really. Okay. So let's move on to 3.7. So real quick, I don't think that this is super important because we're not actually going to use it. Like, you're never going to actually use this software. So there's two different books. There's one thermodynamics book, which is the one we're using, where they use interactive thermodynamics. For another thermodynamics book, their software that is put inside of it in the book is EES, which EES is the only one I know how to use. I've never even opened this, but EES is extremely cool. Essentially, you can solve properties. Like, let's put it this way. There were questions in Thermo 2 where it would have taken me 40 minutes to solve, or 20 minutes, something like that, 20 to 40 minutes to solve. I could solve those questions in less than 2 minutes or 3 minutes using EES. So EES is pretty cool. Unfortunately, I don't have access to it because I'm at home, but at school, EES is there. So here it is right here. Engineering equation solver. Unfortunately, it costs a lot of money to buy that, and I'm not really going to do it. So, all right. Let me see. Let me see if there's anything in here we need to talk about. Okay, so let's do that. I think it's good. So let's do using property tables. Can you guys give me 1 second though? Actually no, never mind. We'll be okay. I'll just wait a second. So it says 3.81 using property tables. So it says in examples 3.3 and 3.4, closed systems undergoing processes are analyzed using the energy balance. In each case, sketches of PV or TV diagrams are used in conjunction with appropriate tables to obtain the required property data. Using property diagrams and table data introduces an additional level of complexity compared to similar problems in Chapter 2. So right here, this is what we're going to be doing, okay? So everyone, if you aren't quite sure about the tables yet, we're going to do another very quick question on tables. Everyone's favorite Paint 3D is back. So, real quick, I'm going to go ahead and put this up in the corner here, and this as well. All right. So let me scoot it in here. All right, so get this out of the way. So it says, a well-insulated rigid tank having a volume of 10 feet cubed contains saturated water vapor at 212 Fahrenheit. The water is rapidly stirred until the pressure is 20 pounds per square inch. Determine the temperature at the final state in degrees Fahrenheit and the work during the process. Okay, so those are our two things that we have to do. So I'll go ahead and we're going to go through with what we have and what we need to find. So really quickly, these are the knowns. I'll go back to using the text tool. I actually think the text tool is just massively better for this. So let's do knowns. So we know that volume 1 is equal to, this is big volume 1, is equal to 10 feet cubed, right? And we also know that, what else do we know? So really quickly, let's read this first sentence again. Well-insulated, rigid tank. So everyone think about what they have just told you right there. What does well-insulated mean to you? No heat transfer. Tanner is correct. So what that means is that inside of this boundary, so look at the screen, inside of here, this is super insulated, which means that we're assuming that no heat transfer is leaving from the water to the boundary. Okay? So heat transfer is 0. And conversely, no heat is coming in, right? Because heat has to travel from the hot to outsides, and we're assuming the outsides are at a normal temperature. So no heat transfer. So we can go ahead and write that down. So Q is equal to 0. Okay? Let's try another thing. So it says well-insulated rigid tank. What does a rigid tank mean? Volume 1 is equal to volume 2. And the reason why that is because this tank right here between phases is not changing volume, because like I said, think of it as a like a propane tank, right, or something. As you pressurize the tank doesn't change volume, right? It's rigid. It's made of, probably some sort of metal, right? I don't know what type, but it's made of a metal, right? And so it's not going to change unless it was put under immense pressure, but it's not generally. So the thing is that it's not going to change size. They are going to be the exact same from one state to the next. It is a rigid tank, and we're treating it as such. So volume 1 equals volume 2. And it also said, this is the most important one, I think. It contains saturated water vapor at 212 Fahrenheit. So what did they just tell us there? They told us what? What is saturated water vapor? So really quickly, since all right, so we have gas, which makes sense. But there's more to it than just that. And we will be talking about that in just a second. So Tanner's got something for me here. Maybe. So we are not past it, but we are saturated water vapor. So everything is water vapor, which means that we are right on the line, on the far right. We are basically right. We are right before superheated. We're still saturated. So which means that this is what I want you guys to know, is that X1 is equal to 1. The quality at state 1, remember, has to hit between 0 and 1, 0 being saturated liquid all the way to the left of the graph. 1 is right at the very end of it. So we are still saturated, but let's put it this way, guys. We are one like mouse chirp from being superheated, right? We are right at the border, okay? Which is good, right? We that right there, that piece of information allowed us to, basically, if you don't get that piece of information, you'll be stuck, because there's nothing else that tells you to get a state point there. And it also said at T1 equal to 212. Okay? So that is where we're at. T1 is equal to 212, which, if anyone knows anything or is familiar with it, 212 Fahrenheit is the boiling point of water at 1 atmosphere. So basically that's what it takes for you to boil water right now from where you're sitting, 212. So it doesn't say atmospheric pressure, but I guarantee you when we go to the tables, it'll say 14.7 psi as its boiling point, or its boiling pressure. So these are the things that we know. But there's actually one more thing I forgot. It says, then the water is rapidly stirred until the pressure is 20 psi. So there's 2 things that we need to figure out in there. So really quickly, what does rapidly stirred mean? Like, what did we have to do for rapid stirring? Like, what is that? It's work. Yes. Something had to be done, right? We had to insert some work. Work had to come into the system. Yes. All right. And then there's another thing. It said pressure 2. So pressure 2 they've given us as 20 pound force per square inch, right? Which I guarantee you that's a pressure increase for sure. Number 1, because we're putting more energy in there, exciting it, and it's getting it further up, right? Higher temperature, higher pressure. Number 2 is that because 14.7 psi is where we were at first, I guarantee you. So this is what we know, right? And what we are trying to find work, and we want T2. So that is what we're looking for, we're looking for work and temperature too. So let's go ahead and put that there. So our first step here, we got to find everything we need to know about state 1. You guys would probably agree we need to find some properties associated with state 1. So let's go ahead and start here. And how I always do it is state 1. So I'll write state 1 out, and I'll be like, okay, we need to find everything. So enthalpy, internal energy, all that stuff, volume. So really quickly, if we go to the tables here, which is our first stop, remember we were given a temperature, not a pressure, so we must go to the temperature tables in English. So let me go and find temperature tables in English. Right here. So this is the properties of saturated water, liquid vapor, temperature table in English units. So we must go down to 212 Fahrenheit, which is right here. I'll extend that for now. So this was the first temperature given, which was 212. Okay. And if we go across, look what I told you, 14.7 psi. So that right there is the boiling pressure. So this is where we are located, is on this line. Now, can somebody tell me which value do we need to grab from the table? Which one is it? Considering that I told you that x is equal to 1 and we are a saturated vapor, which of these values do I need to grab? Stop me when I get there. That one, I agree. Anything else? Nothing? Let's take that one too. And now really quickly, I don't believe we want enthalpy. This is a closed system, right? So we don't want enthalpy. But if it were an open system, we would be swapping. We'd be, instead of getting saturated vapor U, we would be getting this value here. But for right now, we want enthalpy and we want specific volume, nothing else. In later parts, we will be taking entropy, but for right now, this is what we're looking for. Okay, so let's go ahead and grab those two values at 212. So the two values that we are looking towards are these two, 1077.6 and 26.8. Those are our two. So I will go ahead and write those down. 1077.6, okay. So we have U1 is equal to 1077.6 kilojoules per kilogram. And we have little v1 was equal to, I don't remember, but I'm sure one of you might, 26.8. All right, cool. 26.8, and this will be in feet cubed per pound. All right. So that is state 1, right? We have found everything that we really need to know about state 1. The other stuff is not as important right now. Not yet. So we've found state 1. Now we need to find a way to lock in state 2. That's our next goal here. So let me pull this up and then bring this into foreground. So we need to find a way to lock in state 2. So does anybody have any ideas about how, basically let's put it this way, how do we know state 2 is related to state 1? In what way do we know that they are related? Anybody want to take a shot at this one? How are these two states related? Correct. So what he has just said is that because we have a constant volume process, which this is, like I said, this is what that's called. There's constant pressure processes, there's constant volume processes. What we are in is a constant volume process, which means that our volume 1, little v1, is equal to little v2, which is then equal to 26.8 feet cubed per pound, right? So that right there is the main thing that we had to find. If we did not know that, then you're stuck. You will not move on to the next part of the question, at least correctly, because that right there is something that you have to have. Okay, and with that knowledge, we also knew that pressure 2, P2, is equal to 20 pound force per inches squared, right? So now, what would be your next guess as to things that we have to do? Because remember, we still have to find U2 here, right? We have to find internal energy 2. So what would be your guess as to how we do that? Where do we go now? Now that we have pressure 2 and we have volume 2. Remember the steps from last time. What do you think we should do here to solve this state point? Let me ask you this. Do you know if it's superheated? Is it saturated? Is it subcooled? Does anybody know? Because if you don't know, it means that we need to know, right? If you're not sure, it means we need to go prove that it's in one area or the next. So I'm going to go ahead and go do that. So we're going to go really quickly back to the tables. So remember, for stage 2, we were given a pressure, not a temperature. So we need to go find the pressure table, which is actually down here. So here's the pressure table, and we need to go to 20 psi, which, as you guys remember, was step 2, where it was 2. So what we need to find is we need to compare our specific volume value. We have to compare it to what is in the table. So if you slide across here on this row, you will find that the saturated vapor volume is 20.09. Is our value in between 20.09 and 0.01683? Anyone? Our value. Tanner said it was greater than, but you, or no, not Tanner. Tanner said that it was in between. You said it's greater than. It is definitely greater than. 26.8 is definitely higher than 20.09. So this value is greater than the one out here, which means that our value is now beyond that. We are now past saturated conditions. And also there's another way that you could have done this sort of more logically. If we were a saturated vapor before, X1, right? We were, like I said, we were one little mouse whistle away from being into superheated, right? And then they started stirring it up and putting energy into it. Do you think it can go backwards and start making its way to subcooled? The answer is no. We added more energy to it, and it was already on the verge of being superheated, so therefore we put enough energy to make it superheated, right? So you can do that sort of like logically, or you could do it in here, but both lead you to the same place. You do still have to use one table versus another, and you'll get more comfortable with that later. So now we have to go and find U2, now that we know it's superheated, because once again, our value of volume is greater than this one shown right here. We now have to move into the superheated tables. And so this right here, we have to go down to pressure of 20 psi. And what we have to do now is we have to find a volume value that matches ours. So here's the volume values right here. It's this very first column. We have to find one that matches our value, right? And our value is 26.8, if I recall. Or it's 28.6, one of the two. I might be, let me see, 26.8. So 26.8 is our volume value right here. So we have to use this table, and we have to find 26.8 in here. Well, as you guys might see, is that our value is in between these two. It's in between 400 and 500 degrees Fahrenheit. That's where our temperature is, somewhere in between, right? And our internal energy is somewhere in between these two as well. Okay? So there's a couple ways you can do this. This is where interpolation would come into play. I don't have my interpolation calculator in front of me because I didn't get it to work on my really nice one. But what I would do is, if you're not going to do that, which is fine, you don't have to interpolate on exams, but it really makes your answers very close dot on to where the actual one is. But what I would say is this: which one of these is it closer to? Is 26.8 closer to 28.46 or 25.43? Correct. It is fair. It's closer to 25.43, which means, but you know it's not exactly 25.43. So what you could do here is you could just take a nice little guess. And what my guess would be is that I would say that this is like, I don't know, 417 is what my temperature would guess would be, somewhere around like a 420 area maybe, 415. But any of those, if you use that guess, any of those are like decently fine, as long as it's not crazy, right? Like if you put, 490 here, it's very clearly not 490 because you are then right at the border of being the one that's higher. So you just have to take an intelligent guess here. I'm going to say I'll just say 415 here. That'll be my guess. So the temperature I'm going to call it as T2, and we'll see how right I was in a second. So 415. Is what I'm guessing. And our volume value, or not our volume, our internal energy value, I'm going to say, let's do 1153. I'll do that. We'll do 1153. So once again, I just picked a value in between these two. So I'm going to say 1153 for that. So U is 1153. Okay? No harm, no foul but we're about to find out if I'm actually right here in a second anyway. So let's see what they got for their values. So what did they get? Okay, so I was a little off, a little bit. So really quickly, you can see that for T2, they got temperature is 445, so maybe it was closer to halfway than we thought. And it was U2 is 1161. So those were my guesses. I was a little off, but if this is the thing is, if you guys guess these things and they're reasonable, you will get the answer correct. But as you guys can see, there is a danger in doing what I just did, is that we ended up really far off of the temperature answer, right? A matter of, 30 degrees, right? The internal energy one wasn't that bad, but this one was. And so this is the danger in just guessing between the lines of the table, okay? So from now on, I'm actually going to use their answers now that we've, found out that I was really wrong here. Or not too wrong, but enough. So really quickly, these are the things they grabbed from the table. They did T2 was 445 and 1161 for the energy. So I'm going to go back here. Come on. So U2 was 1161. T2 was 445 Fahrenheit. And then I'll put this one as BTUs per pound. Oh man, that's a mistake. Now that I remember doing it, I don't remember doing that, but yeah. So this internal energy value should have the same units as the previous one, and I messed that up. I used the wrong units. So these right here should be BTUs per pound. Because we are in the inferior units. All right, BTUs per pound. All right. So right now we have internal energy 1, volume 2, pressure 2, U2, internal energy 2, and temperature 2. So we've already answered one of the questions. We had to find the final temperature of it and the work. So we've already found the first part. So this first one is gone. We got them. T2's done. Now we need to find work. So we need to find the work of this. And so let's go back to, that energy balance equation that we did. So let's move on down here to the energy balance. So let's write solution here. So the energy balance equation, does everybody remember what that energy balance equation was? In terms of heat transfer, work, and internal energy, what did it read? Use your noggins here. You can write it in the chat if you want. So it basically what it did was it said heat in and work have to, or it's heat and work have to be equal to what? essentially, is what I'm asking. What is this equation? What is the one? This is a very popular equation, by the way, so you should remember this. Let's say Q minus W is equal to U1 minus U2. Right? Does this ring a bell, hopefully? Can I get some yeses in here? No people are still alive? Okay, that's good to know. So, Q minus W is equal to U1 minus U2. And what this is just an energy balance. What this is saying is that the heat transfer, subtracting off the work, has to be equal to the internal energy change as well. So, more or less what this is saying is that there is no other energy either coming in or leaving that isn't heat or work. Nothing else is happening. And also that the fluid's energy is being taken in. So essentially, U1 is the beginning state of the water. We put in some work, and then it is transferred to the second state. So energy is not leaving, it is just being put in to the system, and it's being absorbed by the next state's internal energy, right? That is more or less what it is saying. So this right here is where we're at. Now, if you guys remember from the first part of the question, Q is equal to 0, right? Because it was a very well insulated tank, as they called it. Very well insulated. So we can have a 0 there for that. And now we have work is equal to U1 minus U2. Well, we know both of those values, right? We found them painstakingly, but we found them. We have work is then equal to U2 minus U1. So if we do that really quickly, you will get work is then equal to our values up here, which is 1077.6 minus 1161. And put it in parentheses, and then you add your units at the end if you really want to. But if you know your units, not a big deal. So really quickly, does anybody know what that is? It looks like 17 will take us down. So what? 17 or 16.4 or something like that? Something like that. Whatever it is, I don't know. I'll just pull up the calculator because I'm, lazy and don't want to do that. 1077.6 minus 1161. Wait, did I actually? Oh my god, why did I thought there was another one here. Okay, never mind me, guys. It's 83.4. Wow. That'll read really good on the recording later. So, but specifically though, instead of 83.4, it is negative 83.4 BTUs per pound. Now, the reason why that last part is important, right? The reason why that last part is important is because this is showing a negative sign. Does that make sense to us? Why is work negative here? Yes, we are having to put something in. The paddle wheel isn't just turning itself, right? This thing is not, this propeller is not just turning itself. We have to do it by something. Whether that be you turning it with your hand, whether that be attached to an electric motor, something. It had to be done by something. Which means that this makes sense to us, that the work is negative. It has to be, right? So it checks out that we had our signs right. Now, really quickly, it doesn't, so this is something that I have always argued, but it does not matter this right here. So, for example, if I would have done U2 minus U1, I would have gotten an 83.4. But if you know in your head, if positive numbers make more sense to you, if you know in your head that this is negative work, you can just get an answer here and you can take out the negative and you can just say this, work in. You can specify and just say this is work into the system. If positive answers make more sense to you, you can do that. But you need to specify direction, right? It's sort of like when you used to do forces and statics, where you had to specify tensile or compressive, right? It's sort of like that. You have to specify direction of the force. And so if positive numbers make more sense to you, if you want to do U2 minus U1 and get a positive number, you can do that. You just have to say which way it is. And also, if your signs get mixed up throughout the question and you end up with a 83.4 and you go, oh man, that doesn't seem right, this is work going in, you can just, if you know it in your head because you have good grasp of the concepts, you can say, oh, I just have to add a negative sign, right? You just have to get comfortable with it, and then eventually you can just prove mastery by just knowing. You have to know that heat has to be entering, or like heat has to be leaving, or work has to be entering, or work has to be leaving. You just know, just by the question's design, right? So that right there is the solution. I'll go ahead and click that off, and let me see if that's what they got. So they did. Oh, okay. So they actually found the mass. Let me see if they told you to find. Oh, they said to find it in BTUs. Oh, okay. So we found it in BTUs per pound. Which is not, it's not, this isn't wrong, it's just that we didn't multiply in by a mass. I didn't read the rest of it and say they want it in a specific unit. So this is BTUs per pound work in. So to find it in BTUs, so work in BTUs, you have to find a mass, right? Mass is required. So how they found a mass was how they found it the last time. If you guys remember, since we know volume 1 is equal to what was it, specific volume 1, or so it's specific volume is equal to volume over mass, and so they just rearranged that to get mass 1 is equal to volume divided by specific volume, right? Or little v. I think that's what they did. Let me see. Yep. So right here, they took our specific volume and divided it through our regular volume, and you get 0.373 pounds. They just rearranged the definition of specific volume. And so I will do that really quickly. 10 feet cubed. And I'll put this into parentheses. Divided by 26.8 feet cubed per pound. So if you do this right here, you end up with that 0.378 value that they got. So you get M1 is equal to 0.378, which I think that, or 373 pounds. Because if you see these units cancel, the feet cubes go away and you're left with a pound on top. And then what they did is they take this number and they multiply it in here. So if you do that really quick, you would get your work in BTU to be equal to 0.373. So make sure you see what units they ask it for in. I didn't look because I was careless, but hopefully you will not be, because that could be a difference between an answer being right and wrong. So that right there is that. And then if you move down here, you get work in BTU is equal to that, which if I had my calculator out, which I don't have it out again because I get rid of it every time, you have 0.373 times 83.4, and you get 31.1, which is exactly what they got. 31.1 BTUs. Okay, so they got 31.3, but that's due to rounding errors, all right? 31.3, same thing for me, okay? So hopefully that makes sense to you guys, because this is probably going to be one of the last times that we sit down and do a lot of work in the tables. I'll still go through it on screen, right? But I'm not going to painstakingly explain every step, because after this part of the class, so let me go back here. So the reason why we did it today was because the only 2 chapters covered today were the EES, like it's supposed to be like how to find properties on a computer. But since we aren't going to use that software, we just did an example question, right? But in the future, for the rest of this class, essentially, I will not painstakingly go through every step. I'm going to have to assume that you guys know it to some degree, right? So hopefully you guys get that. And now really quickly, before you guys are out of here, I'm going to show you this really quick. So this is the PV diagram and the TV diagram for what we just did. All right, so let's go through it really fast. So our first pressure found on the table was 14.7 psi. That is just simply because our first temperature is 212, as you can see here. So this is the TV diagram. This line is 212, which was the first temperature given. We were also given x1 is equal to 1. So really quickly, that's right there. And the reason why it's right there is because, remember, they said that this was saturated water vapor. So saturated water vapor had to end up right here. Okay? So state 1 ended up right on this line here. And now recall that between these processes, it was a constant volume process, right, when we started putting work in. So our volume does not change. So we go straight up here. Right? Straight up. Oh, man. So we go straight up to the next stage, dash, 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 to a higher temperature and pressure. Because remember, the second thing they gave us was the pressure, which was 20 psi, right? So now we can scoot over to here. So these two graphs are kind of used in conjunction with each other because remember, between stages you were given different things. The first stage you were given temperature, which is this right here. And it brought you here onto the graph. But on the next stage, they didn't give you temperature, they gave you pressure. So then you can go over here. Although they both are they're very similar, except the direction of the constant pressure and temperature line. So first one, we go up because volume stays constant. And then we go to the 20 psi line because we know that's the final pressure. And we find this temperature. And remember, lines of constant temperature go down like this. So those are these two lines. So T2, which we remember was 445, is that line of constant temperature. That one's 212. And also recall that because we added energy from stage 1 to stage 2, since stage 1 was already saturated vapor, there is no way you can go from saturated vapor to not being superheated while adding energy. Because think about it. If we did that, how could we do that? Like, if we added energy to this thing, we would have to be like, if you added energy to it, I don't even know how it would even make sense. While keeping the volume similar, there's no way. Look at the shape of the graph. While keeping the volume similar, there's no way to get under here again after adding energy. It's impossible. So, that is how that one worked. So this chart right here for your next homework, and I think the one you just turned in, you had to make a few of these. How comfortable are you making these? Were these like, difficult? Annoying, probably? Oh, you didn't have to do any charts? Okay, so for the third homework, you will have to do charts just like this, and it'll ask you to do TV and TV and PV diagrams for your questions. It'll ask you to draw these out. And so what you're going to have to do is for that is, once again, you have to follow the little steps. You're going to have to first find the state point, right? First find the state using the things they gave you, whether it's saturated vapor, saturated liquid, a mixture of those two, superheated or subcooled. You're going to have to find where it starts. Then, using the information given about state 2, you are going to have to find state 2's location on the chart. And by the way, your questions for this next assignment will be a lot like this. So you'll have to do things like this question that we've just done. And they're even a little more complicated than that too. So for example, this right here is a very common question for this chapter. So if you need help with a question, there is a question on your homework that has you do this. It tells you process 1 to 2. It says the water is cooled as it is compressed to a constant pressure. So you have to once again take out some information here. So water is cooled. That means that heat is leaving, right? It is being compressed, which means that volume got smaller, right? Because obviously if something is being compressed into a smaller area, volume had to get up. And as well, or volume had to be lowered and pressure had to go up. And then they gave you the saturated vapor state as the last one. They said, okay, it's also saturated vapor. So you have to extract the information out of these statements. And so that means you need to find state 1, state 2. Then you have to find state 2 to state 3 as it tells you more information. This question is on your homework, not this exact one, I don't think, but this type of question where it will give you two separate processes, a process from 1 to 2 and 2 to 3, and you have to extract information and solve it, okay? And so what it ends up looking like is something like this. It's a little piston cylinder. The water compresses as our volume moves slower, our pressure gets higher, and then some more heat leaves, right? So if you do need help, just know that there is a question in the book that is extremely similar, and it is example 3.4 on page 120 or 110, I think. Let me see. Yeah, looks like 110. So, are there any questions about that before we get out of here? I would start looking at your homework now because some of those questions are quite difficult. Not quite difficult, but you know they ask you more. The curve of requirements has now went up. It's not simply what direction is work or find quality. You know what I mean? It's now more of what we just did, which is extract information from the question and then use that information to move from stages 1, 2, 3, right, 4 if need be. So you guys are going to have to do that now. It's all about taking they don't just tell you a lot of times. It's usually things that are very subtle, like compressed. They say the word compressed at a constant pressure of 10 bar, right? You see? They will tell you things like that, and you then have to decide what that information means. And the reason why I should say you say it start now is because if you need help, I would gladly answer the questions you require. But don't come to me on Sunday at 2 o'clock going, well, I'm on question 1. I need help. Right? Because then I will feel bad for you, but not that bad. Let's put it that way. So I'm going to show this on the screen one more time before I stop the recording. And hopefully that made sense as we move through that question.